Hello. Today we will continue with the fourth module. Till now in this we have studied MOSFET as a switch, how MOSFET will behave as inverter, or how it can be used to design AND gates and other logic circuits. So then using all this, how subsystems are developed. The main intention behind learning all this is finally we have to produce an IC for a particular application. And this IC, which is developed for a particular application, is usually called application specific IC. This application specific ICs can be developed using two methods, either semi-custom or full custom. In full custom, the components, all the components, the designer, he himself will design right from starting from the behavioral specification, taking the specification, then breaking down into each level, then going down to transistor level. Every step the designer he himself will design and finally get the product. This product, full custom product, will be very compact, will be very efficient. Whereas in semi-custom, the designer will take the pre-built modules which are already being tested. Those modules he will take, compile them, connect them together, and he will get the desired IC. This is not as efficient as full custom, but they work. But what happens here in semi-custom is the cost and time will be less, whereas for a full custom, the time required will be more because the designer has to do everything by himself. He has to design fully by himself. The other way, once it is designed, it will be only used for that particular application. You cannot reprogram. Whereas the other type of ICs are user programmable. That is, on the field for that particular application, you can reprogram it. So that kind is programmable logic device and field programmable gate array, FPGA. This is the one which we will have to study, FPGA. And PLDs, programmable logic device. See, under programmable logic devices, you have factory programmable devices and field programmable device. Factory programmable means these are programmed in the factory for the particular application and they come. Usually programmable logic device, they have uh, many arrays of AND and OR gates, and they using that arrays of AND and OR gate we program for a particular application. So these programmable ICs are standard ICs that are available in standard configurations. And programmable ICs can be programmed to create a part of customized ICs to a specific application. Okay, these ICs contain large number of gates of AND and OR, and also it will contain flip-flops that can be configured or it can be programmed by the user to perform that particular application. And as I said, factory programmable device means these are programmed in the factory and they come. You cannot do anything on the field. The programmer cannot do anything. He has to use the one which is already available for his application. Whereas field programmable device means he can take these programmable device and according to his program or according to his application, he can configure these ICs. Under this, you have simple programmable logic device, complex programmable logic device, and field programmable gate array. Under simple programmable, again you have under this simple programmable logic device, you have PROM, programmable read-only memory. Here, read-only memory is permanent. Programmable read-only memory is you can program it according to your application. Then programmable logic array, programmable array logic, and the generic array logic. The generic array logic family, it consists of electrically erasable programmable device designed using lattice semiconductors. Actually, it is similar to a PLA, but it can be reprogrammed and it can also be erased. Now, coming to this field programmable devices. See, field programmable device means it is an integrated circuit used to implement digital hardware, and it can be designed by the user for a particular application where the chip can be configured by the end user to to realize different designs. He can decide what he has to program it for. The programming of such a device often involves placing the IC into a special programming unit, but some chip can also be configured in system. See, if you have done the lab, HDL lab, and in HDL lab we have programmed this, you whatever program you write, your Verilog program or PHDL program, you dump it into the FPGA kit using this flash, and then you check all the outputs. That LED glowing according to your gate or all that, you must all that you check in that. So the program has to be dumped using, it has to be passed to the FPGA using some chip or special program, and you can verify your output. So this you have already, that is, you one particular for lab you have used it, you can just recollect how you have done these. And in the simple programmable logic device, they have just arrays of and it's a simple structure. It will have arrays of and or which can be programmed. And in complex programmable logic device, it consists of arrangements of multiple and or arrays in blocks. Here it will be just simple and an array, whereas in complex there will be many blocks of and or arrays. Field programmable gate array is an again field programmable device which allows high logic capacities, very high logic, very high end designs can be complicated designs can be programmed using FPGA. Coming to simple program logic device, under this you have, see here, coming in simple program logic device, you had the PROM, PLA and PAL. So what do you have? Again three kind, that is programmable read-only memory, programmable array logic and programmable logic array. What is this programmable read-only memory? It has, see, it has a fixed AND array and programmable OR array. Again, as I said, these programmable device will have arrays of AND and OR, and if in programming them, that is connecting or not connecting the inputs to them, will give a particular output according to, if you are writing an equation a and a b plus c, connecting wherever you want, you have to connect the input a b to an AND gate, then the output has to be OR with c. So that connection when you have, you get the particular output, so that you use only AND and OR gates. So here in this AND gate, in this particular programmable read-only memory IC kind of ICs, the AND array will be fixed, whereas OR can be programmed. See here, this is an application. This is for a PROM. Here you see you don't have a fuse here. Programming here means it is fuse or a switch. You connect a switch, it will get connected. Switch means what? Again, refer to your MOSFET. If you give a gate signal, the switch is on. If you remove the gate signal, switch is not there. So if I have a switch, you see here you have a fuse. So if I give an input, I can consider this as a switch. If I give a gate input, this line is connected from here to here. There is a connection. If I have a, if I use a MOSFET here, if I use a MOSFET, from here to here, there will be a connection. If not, there will not be any connection. So it is like, next. Similarly, whereas here, if you see here in AND gate, so such fuse are not there. It means AND is fixed, whereas here this OR can be programmed. You have programming is, it means if you connect this fuse, there is a connection. If not, there will be no connection. Next is the PAL. Okay, PAL means programmable array logic. In programmable array logic, AND is programmable but OR is fixed. See, AND is, you have fuses. Again, you can consider them to be switches. If I give the gate, the switch is connected. If not, it is not connected. Whereas those fuses are not here for the OR gate. Here they are fixed. Here, wherever you want the input, you have to connect the fuse. and the corresponding output goes to the OR gate, and OR out, this is fixed here. Inputs are fixed, you don't have a fuse. Next, coming to PLA, programmable logic device. Programmable logic device, here both AND and OR arrays are programmable. See here, you have fuses for both AND as well as for the OR structure. So here the input is connected. X1 is connected. X0 bar is not. X1 bar is not. X2 is connected, whereas the other inputs are not connected. Here again, connection is there. Here connection. So wherever you want the connection, you connect the switch or connect the fuse. Else you don't. Here also, here you see the fourth is not connected. That means you need not connect that input to the OR gate. The difference between PLA and PAL is, what is PLA? See, this is PLA. Logic array means both the gates are arrays are programmable. PAL means it is only one. Which one is PAL? This is PAL. That is, you have only the AND which can be programmed or is not. So, in what is the difference? PLA is more flexible than PAL, isn't it? Because you have both the arrays which can be programmed. So PLA is more flexible than PAL, whereas it is costlier because you have to have fuses for both of them. Obviously, it becomes costlier. But here, this is more flexible, and whereas PLA is little slower compared to PAL, and this when it comes to availability, the PAL is more readily available in contrast to PLA, which is not easily, this is not easily available, whereas you can have PAL, which is very easily available. So this is PLA, or programmable logic array, wherein you have both AND and OR gates. So here in two markments, you have connecting, you have a switch which will connect the X to the AND gate. So wherever you want the connection, you just mark it by an X. Usually the switches will be like a transistor. See, this is a transistor. If you have a switch like this, this represents, see, this is a switch here. They're representing it like this with the slant line between this with the vertical line as well as with the horizontal line. There is a slant line which represents the switch. What is the switch? See, there is a horizontal. It is nothing but this NMOS transistor. As we said, if we give the gate input, the transistor is connected. There is a connection between. This line will be pulled. If you make this one, this line will be pulled to ground. If not, this line is at VDD or at high input. If this is connected to VDD, drain is at VDD. If I give gate here, if the input line is 1, then output will be pulled to ground. If you have a connection like this, from if the connection is down like this, it means this becomes the input and the drain is connected. If this is 1, the drain is connected to high output. So if this is 0, drain is connected to high. If not, it will be pulled down to ground if this is 1. So now let us take an example to realize an PLA for this function. Okay, if not, using the mean terms, they have got this using the K-map. Okay, we have 4 inputs A, B, C. Sorry, 3 inputs A, B, C. And we have 4 outputs here. So the first F naught, let me just take this in first F naught is A bar, B bar plus A, C bar. General way, the first, see here it is A bar, then it is connected to B bar, then A plus A, C bar. These two are given to the first OR gate, you get the F naught. Similarly, F1, B plus A, C bar. It is the second one. C, it is connected to B plus C, A, C bar. It is given to F1. Similarly, you can check for the other two. The same thing can be implemented using NOR implementation, NOR logic. So you know that a NOR gate can be represented using an AND gate with input bubbles on the input side. So this is an equivalent circuit. Okay, suppose I have a structure like this. Okay, using NMOS, if I have to represent a NOR gate, I have 2 NAND gates here with the input X1 and X2 given to the gate. When X1 and X2 are 0, output, this 2 transistor, they don't conduct. So Z is high, connected to VDD. Suppose either of them is equal to 1. If X1 is 1, this transistor is on, Z is pulled down to ground like this. Z will be pulled down to ground. Z will be pulled down to ground like this. If not, if now X is 1, Z will be pulled down to ground like this. If both are 1, pulled down to ground. So what is it? It is 1. So it is, yeah, 1, 0, 0, 0. So what is it is 1. Then for 0, 0 it is 1. For rest all case it becomes 0, 0 and 0. So this represents a NOR gate. So Z is nothing but x plus x1 plus x2. NOR means it is whole bar, or I've just written it as x1 plus x2 dash here. Okay, so that using De Morgan's I can write x1 x2 x1 plus x2 whole bar is x1 bar into x2 bar. So it is nothing but your NAND gate operation. Then this is, yeah, AND gate using your bubble at the input. Not NAND gate, it is an AND gate wherein it is bar x1 bar and x2 bar. Now if I have to get A bar B bar, see this was the input A bar and B bar for the first one. If I have to get A bar and B bar using this logic, here it should be x1 and x2 means you have to pass it through an 2 inverter. A, it becomes A bar here, then A bar of bar is A, that is passed through this, and even B is passed like this, you get A bar B bar. Here it is A into C bar, and that again is given to a OR gate, and then it has to be it has to go through a inverter, and you get the output F. This is similar to this logic. This is NOR, and this is equivalent and OR. This is a NOR. This represents, see, this represents a NOR equivalent. Here, this represents NOR. Okay, this is also a NOR circuit. So NOR, this is equal to AND OR circuit. The same using this, the whatever we had implemented in this structure can be implemented using this. See here, as I said, it is output here will be A bar B bar, because only when these two is 0 the output is high, else in all the other case output will be 0. So it is A plus B. It is, what is this one you get A plus B. It is A plus B whole bar, A plus B whole bar, which will be equal to A bar into B bar. So that is what we have got here. Similarly, here it is going to be the same for the second line also. And that is passed, this is OR. And if you remember here, see, it has to, after this finally it has to go through an inverter. So it goes to an inverter to get the final output F naught. So this is implementation using NOR logic, a PLA implementation using NOR logic. Next, coming to the complex logic, programmable logic device. As we said, it has many layers of AND and OR arrays. It is not just one layer. It will have many arrays of AND and OR arrays. Next is FPGA. We'll continue FPGA in the next class.